Hello, my name is Megan, and this is my research project called Effects of UV-A Irradiance from LED Lights and Fluorescent Lights on Root Elongation in Brassica rapa. So this is my introduction. So it's widely known that roots are vital for the plant as they have four important functions for the plant that include absorbing and storing water and nutrients. It supports and anchors the plant to the ground, and it translocates water and minerals to the stem and leaves. However, the lesser known function is that they are able to also absorb light from underground through their photoreceptors. So the threat, however, to these roots, among others, is the UVA radiation, which accounts for 95% of the UV radiation that reaches the Earth's surface, as it is able to pass through the ozone layer. It's detrimental because it's able to damage DNA and proteins of the plant cells, and it often reduces photosynthetic efficiency. In this case, in my experiment, I'll be measuring UVA radiation through irradiance, which is essentially the measure of radiant energy emitted per area. So photoreceptors, to get more specific, the reason that they're important is that they're able to protect against UV radiation. However, the problem is that higher irradiance from UVA radiation can inhibit the productivity of photoreceptors, which renders roots vulnerable to radiation and thus susceptible to damage to their DNA. For example, in Brassica rapa, which is the plant I was working with, and Arabidopsis thaliana, which is often the model organism in relation to photoreceptor research, cryptochrome 1 is the photoreceptor largely responsible for absorbing blue light and UVA light, and so how it works is that it receives light through the soil or the vascular cylinder, and then it absorbs and detects the UV radiation, which activates flavonoid accumulation pathways. And these flavonoids and phenolics, which are the UV-absorbing compounds, thus accumulate in the roots. And then the flavonoids and the phenolics are able to absorb the UV radiation in the UV-A range for photoprotection, which thus streamlines the photosynthetic processes and protects them. However, in previous studies, flavonoids only interacted with irradiated DNA and UV photoproducts within the DNA, and they noticed that intense UVA exposure could lead to decrease of flavonoid levels. While Arabidopsis thaliana is the widely studied genetic model for photoreceptors, as they include the ZTL-LOV domain family, which includes cryptochromes, phytochromes, and phototropins. I used Brassica rapa because it was more readily available, and it was closely related to Arabidopsis thaliana. My rationale was that Brassica rapa is widely cultivated for its roots and seeds. It has many culinary and medicinal uses, as, for example, it's used in cancer treatments and as poultice for burns. And it's a widely consumed vegetable around the world, and it's also known for oil production. But there was lacking research on UVA radiation's effect on phenolic accumulation and root growth on both Brassica rapa and on just in general. In contrast, there was a lot of research on UVB radiation's effect, and also light-mediated root growth corresponding to photoreceptors was very limited as well. And then I wanted to highlight the UVA radiation effect from indoor farming technology, because indoor farming is a growing industry due to climate change. There will be increased levels of the environment's UVA radiation exposure. So it's crucial that if we were to switch to indoor farming, we understand which light sources are better and have less UVA irradiation and thus are safer for the plants. And so with my research, I also wanted to be able to identify the plant responses to indoor farming technology's UVA radiation. Specifically LED and fluorescent lights. So my hypothesis was there would be longer root lengths in Brassica rapa grown under LED lights compared to those grown under fluorescent lights. And my objective was to observe the effects UVA radiation from indoor farming light sources such as LED and fluorescent lights had on root development in Brassica rapa, which could also go to show or be indicative of how effective the photoreceptors were in comparison between these two light sources. So my assumptions were, it was assumed that the research was not subjected to bias and was value-free. My hypotheses would be tested in a cause-effect way, and that there would be some external influence on the plant growth beyond the artificial light sources or the indoor light sources that I used. So my materials included of seeds, brassica seeds. I used perlite as my planting medium. I was able to construct my own tank systems that were clear out of acrylic panels, clear vinyl tubing, screw posts, and wood panel holders. And my equipment, for building the tank system, I used an electric drill and a T-square, and the fluorescent lights and the LED lights were the light sources, and my phone was to document the process. The mechanical timer was to set the photoperiods for each light source to 16 hours, and then the Vernier UV-A sensor helped me measure the UV-A irradiance from each light source. The dowel was used to poke holes in the planting medium for seed placement. My facilities were both located in my high school. Specifically, I constructed my tank system in the technology lab, and I conducted the experiment in my research lab. So my setup procedure, I was able to make a tank system, and I used bandsaws, and I drilled holes into each panel for each. And each tank system had 2 panels, and they formed a U, which I lined with cleared PVC tubing to support both the perlite while providing an airtight seal. And I used screw posts to connect the 2 panels and compress the PVC tubing between the 2 panels. And I repeated that, so I had 2 tank systems, 1 for each light source. And then I put perlite planting medium in each clear tank system up until 1.5 inches from the top of the tank system. And I set the lights with a mechanical timer, and I let it, both the tank systems set under a row of fluorescent lights for seed germination. And these are graphs of my tank systems, and those are the setup images. Following that, I measured UVA irradiance using a Vernier UVA sensor, which I later will have a table showing the values. During the growth period, I watered them each day with 500 milliliters of water. The growing period was only 2 weeks, and I measured the root lengths afterward. In data analysis, I created 2 error bar graphs, 1 for each tank system, and I also created a graph comparing the mean or the average length of the roots between the 2. And I conducted an independent one-tailed t-test against an alpha value of 0.05. My findings and data regarding irradiance came out that the LED light had very little irradiance, UVA irradiance, that the sensor only registered 0 milliwatts per meter squared. And for the fluorescent light, it came out to 13 milliwatts per meter squared. So there is a stark difference between the two, although some might argue it's little, there is still a difference. So regarding the root lengths, there were longer roots in the Brassica rapa grown under the LED lights compared to those grown under the fluorescent lights. In my figure 5, you can see that it's quite distinct in the pictures. And in the raw data table, I have them measured in centimeters, and the lengths under the LED lights are consistently longer than those under the fluorescent lights. This graph displays the mean average root lengths for each light source. And it's quite distinct that the LED lights had longer average root length. In my data analysis, I used a independent one-tailed t-test, independent because there were separate sets of Brassica rapa for each set of light sources, and one-tailed because it tested a hypothesis that specifically stated one mean would be specifically larger than the other. And that was my summative data table. And then these are my error bar graphs. There were no outliers. And in my conclusion, there were significantly longer root lengths in the Brassica rapa grown under LED lights. This result encourages the use of LED lights over fluorescent lights in the case of indoor farming and cultivating Brassica rapa indoors, because it did have a lower UVA radiance. This could show and go to prove that go to show that lower radiance might translate into a healthier root and overall healthier plant growth. It seems that higher UVA radiance from the fluorescent light stunted the growth of its roots. And this could contribute to UVA research that is often lacking, or that is lacking now. And my plans for further research include, I would have 2 improvements for my clear tank systems. One is switch from the plastic tubing to a more waterproof airtight seal to prevent the leaks and to keep water consistent. Should devise a method to easily differentiate the roots from the perlite planting medium because the colors were too similar. And for photoreceptor reprogramming, would encourage taking skin photoreceptors and sort of having biomimicry of these photoreceptors in plants.